Channels, contexts, and wait groups are the three most important primitives used to coordinate Go routines in Go. But there are a bunch of other tools in the standard library that should definitely be on your radar. If you need to brush up on the big three, you can check out my concurrency basics video. But otherwise, let's talk about the often forgotten concurrency primitives that Go gives you. The first and most important concurrency primitive I'll cover today are mutexes. Go has two implementations of a mutex that are both defined in the sync package of the standard library. And there's a link in the description if you want to see the actual documentation. The first mutex is just the regular mutex type. And I'll set up a simple example to show you the problems you can solve with the mutex. We'll start with a wait group, a counter variable, and a function that will increment the counter. Then we'll set up 1,000 Go routines that will each increment the counter. And last, we'll wait on the Go routines and print the final result. The issue here is that I'm writing to a shared variable from multiple different Go routines. So we end up with a race condition. So when I run this code, you see we get a different result every time. And as an aside, it's super useful to use Go's built-in race flag for checking if there's a race condition like this. And you can run the race detector using the race flag when you run your code using Go run, or if you're testing or building. So now we have a race condition we need to solve, and we're going to use a mutex to do it. So first we create the mutex. Then whenever we write to the shared counter variable, we need to acquire the lock owned by the mutex. And then once the operation is complete, you need to call unlock. The lock call works by blocking the Go routine until the mutex's lock is available. And unlock just releases that lock so another Go routine can pick it up. One important point to wrap your head around is that the lock is on the mutex, not on the actual counter variable. So nothing stops you from writing to the counter at the same time in another Go routine. And it's up to you to make sure that the same mutex instance is used to synchronize access to the shared state. And because of that, you should never copy a mutex after you start using it. So if you're going to pass it around, just use pointers. And that same rule applies to pretty much everything when dealing with concurrency. So it's best to just use pointers unless you have a reason not to. All right, the last method on the mutex struct is called TryLock. It will attempt to acquire the lock, and instead of blocking if it can't get the lock, it will just return false. Then you can check the return value and see if you're allowed to access the shared variable. You likely won't need to use this, but it is useful to know that it exists. Okay, our next primitive is a read-write mutex. It's pretty much the same as a mutex, but it allows multiple simultaneous readers. So let's say I have another function that reads from shared state. And we'll spin up more Go routines to run that. If I use the regular mutex here, then all of the reads will block all of the writes. So when I run this code, most of the values we read won't be repeated because only one read is happening at a time. But in this case, we only need to block writes while we're reading. Multiple reads should be able to happen at the same time. So instead of a regular mutex, we use a read-write mutex. For writing to the shared state, we'll use the same lock and unlock functions. But when we read, we'll use rlock and runlock instead. Now when we run this, we get way more repeated values printed out because more reads can happen in parallel. There are also TryLock functions on the read-write mutex type, and they work the exact same way as the TryLock on the regular mutex. And again, docs are in the description if you want to check those out. All right, next up is the Once struct type. It's also defined in the sync package, and lets you ensure that a specific action is performed only once. So let's say we have a custom type that represents something like a database connection. Then we'll have a global variable for the store and an instance of the once type. The store only needs to be instantiated once, but multiple goroutines need access to it. So I'll make a function that uses the once type to instantiate the store the first time the function is called. Once only has a single method called once.do, and whichever function you pass to do will only ever be executed once, and then we return the store. So when the function is called for a second time, the once.do is skipped over, and the current value of the store is returned. Then in the main function, I'll set up a few goroutines that will all call the getStore function. And then we'll print the store. And now when I run this, the number in S should be the same for every print line because the store is only initialized once. And nice. And this is also one way you can implement a singleton if you want to think about it in those terms. One extra caveat I want to mention with using once is that if your function panics, the once instance will still consider that function to have returned. So you still can't run it again, even if you resolve to the panic. There are also 3 helper functions in the sync package that wrap the once type and just give you a different syntax to interact with it. But before we get to those, if you're finding this helpful, then consider subscribing for more. All right, the first helper is sync.Once func, which accepts a function to execute and then returns a function that wraps your function with a once internally. So no matter how many times I call this function, the wrapped function will only run once. So when I run this, we only get the single printed message. The next wrapper is exactly the same, but it also saves and returns a value. Now, every time we call the wrapper function, you'll get the return value that was saved the first time you called it. So when I run this code, you can see that the inner function is only called once, but we get the same value for A, B, and C. And the last wrapper is the same as once value, but the wrapped function can return 2 values instead of 1. Then we can call the wrapper function multiple times. And again, when we run this, the inner function only runs once, but we get the same output each time we call the wrapper function. Okay, next up is the sync.Cond type in the sync package. Cond stands for condition, but I am not a huge fan of this one because the name is a bit misleading. On the surface, the condition type looks like a wrapper that lets you wait for some condition to be true before proceeding in a goroutine. But it actually doesn't do that internally. You need to do the Boolean checks manually. So what it really does is let you wait and block a goroutine until you receive a signal that the underlying state your condition depends on changed. And then when the state changes, you need to manually check if your condition has been satisfied. And if not, you start waiting again. And if it has, you can continue. All right, so each condition instance needs a mutex or a read-write mutex. And you are responsible for calling the lock and unlock methods when you check shared state. Then we can create the actual condition variable using sync.New.Cond and pass in the mutex. Now, the first thing you want to figure out is when to send a signal to the condition instance. And generally, you do this when the state you care about changes. So in this case, every time this shared counter updates, I'm going to send a signal to the condition instance. So in a goroutine, we'll acquire the lock, increment the counter, send the signal, and then unlock. One important point to note here is that calling signal will only wake up a goroutine if one is currently waiting. The signal isn't remembered for go routines that might wait at some point in the future. And then another important point is that the signal can only wake up a single go routine. So if you have multiple go routines waiting on a condition, then signal is not the best method for that. So next, we need to actually wait on a manual condition that uses the shared counter state. So we'll spin up a go routine. And because we're checking the shared counter state, we need to acquire the lock first. Then we write our condition in a for loop. So here, if the counter is less than 100, we'll call condition.wait, which will put the go routine to sleep, and then release the mutex lock so the counter can be updated and read from other go routines. Now, when the signal is called, it will wake up a single waiting go routine. So every time we increment the counter here, this go routine will wake up, reacquire the lock, check the condition again, and if the condition is still true, we'll continue to wait. Otherwise, we can proceed with the rest of the go routine. And when I run this, it should all work. Nice. So like I said, if you have multiple go routines waiting on the same signal, then signal is not the best method to use. So instead, you can use the broadcast method. And this will wake up every go routine that's waiting instead of just a single one. Okay, the last thing I want to cover in the sync package is a concurrency safe map implementation. And it's basically like a native map in Go, but with all the mutex locks done for you. And according to the docs, there are really only two situations in which you would use a sync.Map. First, if your map is like a cache that only grows and your keys are only written to a single time, but read from multiple times from different go routines. And second, if your different go routines are writing or reading from separate key sets that don't overlap much. So if your go routines need to access all the same keys and are writing to each key more than once, then it's better to just use a regular map and handle the concurrency logic yourself. All right, let's do an example. First, we create a map instance, and then there's a bunch of methods we can use. First, you write to the map using store, and then you can read from the map using load. And the load method also returns a Boolean that tells you if the key was found in the map or not. So we can check if the key wasn't found. Then you can delete a key using the m.delete method. And m.clear will delete all entries in the map. All right, let's repopulate this. And the next method is called map.range. And it lets you do a range loop over the map because Go's native range won't work on a struct type. And if you return false from this function, the iteration will stop there. So we return true, so the iteration continues. One caveat with the range function is that even though it's concurrency safe, updates may still be made to the map while you're ranging. So there's no snapshot that will stay consistent through the whole loop. So that's just a small gotcha to be aware of. And that covers all the basic map operations, but there are a few more methods with some more specific functionality. So things like load or store and compare and delete. For the full list, check out the docs in the description. One more thing I'll note before we move on to the atomic package is that the sync package also has a pool type, and it lets you reuse allocated values. It's concurrency safe, but it's not really specifically used for coordinating Go routines, so I will leave it for another video on performance optimization or garbage collection. Okay, the last thing I want to cover is the sync/atomics package. And there's way too many functions to fully cover it, so I'll just go over the basic concepts, and you can check out the full documentation in the description. The first thing it has are a bunch of wrapper types that wrap native types in Go and make them concurrency safe. So it's similar to the map type from the sync package, but for more primitives like ints and booleans. And the advantage of using these over something like a mutex is that they're much lighter weight and generally more performant. So let's do a Boolean as an example. First, you create it like you would any struct, and then we can set the value with the store method. We can read the value with the load method. You can extract the current value and set a new value using the swap method. And last, you can use compare and swap to say if this first value matches, change the value to the second value. So that's the concurrency save Boolean type. And the atomic package has other types for int32s, int64s, uint32s, and 64s, and then pointers and uint pointers. And the numeric types have a bunch of extra methods that let you do things like concurrency safe addition. Then there's also a generic value type that lets you store any type inside of it. And apart from the types, the atomic package has a heck ton of helper functions. For example, you can use atomic.addInt64 to apply an atomic operation to a regular int64 variable. And those are all the often forgotten about concurrency primitives in Go. Links to the code and docs are in the description, and I highly recommend at least giving the sync package a once-over because there's a ton of stuff in there. If you found this video helpful, consider subscribing for more. And as always, keep breathing, keep building, and I'll see you next time. Peace out.